All right, welcome to week 9 workshop, CIV3SD1. We are starting on slope deflection matters. We yesterday take a lectures on slope deflection matters. We mostly covered the theory and explained the fundamentals of the slope deflection matters. After completing these weeks, you can take questions 3 in your assignments, which is the based on this week slope deflection matters. As I mentioned, if you follow week by week lectures and workshop, you can smoothly finish the assignment without any overload. They are just half an hour, 1 hour works after you complete the lectures and workshops. Pretty straightforward they are, and you can use again space case to compare your answers. If your answer is not matching, you can go back and correct yourself. So there is no way you can lose the marks in the assignments particularly. Now let's start solving these slope deflection matters. Now slope deflection matters, as I mentioned, comes after is part of the deflection matters. We're going to teach three deflection matters. First one is slope deflection matters. Next week is moment distribution matters, and the last one is the stiffness matters. So those three are sitting in the bucket of deflection matters. Last week we studied force methods. All these force method, displacement methods are used in solving the indeterminate structures, meaning that your structures are indeterminate, meaning there are more unknowns value than equilibrium equations. You can't solve those questions right now that we are talking, not solving by these equilibrium equations, as you know from last week. The advantage of these displacement methods that it can be used when you have multi-spans, like degree of indeterminacy is quite high. Let's say if you have a let's say if you continue this beam with the rollers, displacement methods are quite useful in that sense. Force methods will have some limitations. It can be useful when degree of indeterminacy is 1, 2, because then you will have a simultaneous equations to solve that one. But displacement methods are quite powerful. These displacement methods are invented in 1914. We still use it, but because it's very fundamental, it's give you that sense of and feelings what is happening actually internally, and then you can build those fundamentals of those. So I think the solving the example is quite straightforward, just the maths. And there are steps that you always follow. You always find this one first, then you do this one second, then you do third this one. You don't need to remember the equations. All the equations are there, and I will tell you where these equations are. If you want more details about the theory and where these equations come from, look at our lecture notes. Yesterday we covered most of them. And if you have not able to attend that one, the recording is on LMS. So I'm not covering the theory here. Let me, and of course we are recording. So if you miss any of the details, you can of course go back and refer it. You more than welcome to just stop me and say that, hey, this is going too fast and does not make sense. It's waste of time for yourself and myself. So we don't want to do that one. Just stop. Say that, okay, where this value is coming from and where this equation is coming from, we can go back and refer it and slow down, okay? But as the time progresses, those last examples I will do fast, okay? But first 1 or 2 I will go slow, but still if it is fast, you let me know. Now determining the internal moment of the supports A, B. So just basically wants to find the reaction forces of the beam with the stiffness EI for each spans. The different stiffness are given here. And then draw the SFD and BMD. This is the final exam question in 2017 for the students. So for the reference that is there. So students who are in 2017 with us, they have solved this example in their final exam. All right. So step number 1, we find. Let's say we do the fix and moments. Right, yesterday we discussed that all the internal supports will be clamped. All the internal supports will be clamped, meaning they will be turned into the fix. So in these figures, what we're going to do it, and we can't touch A and we can't touch C. They are untouchable. OK, we can't change it A and C, but B is the internal support. So we make them fixed. Why we make the fixed? We covered in the last yesterday, right? You remember that one. So we fix that B. It's not a roller anymore. We said it's B. Right. So if it is fixed, then I can draw this one. A, B, 60 kilonewtons, 2 meters here, 2 meters here. You with me? This one. And then I can draw BC. B, C, UDL load of 20 kilonewton per meters and 4 meters. You with me, right? I just take it segment AB, segment BC. Don't touch A and C. A is fixed, A is fixed. C is roller, C is roller. Internal, all fixed. Should not have. If it is give you multi-span, you can repeat this process for multi-spans. OK. All right. Then you said on this end, we have fixed end moments of AB and fixed end moments of BA and fixed end moments of BC. Right? Why we do fixed end moments? Because slope deflection methods does not like that the load is coming on to the members. Look at these 60 kilonewtons coming on to the members. Slope deflection method does not like it. Slope deflection method like this. Let's say you have these kind of if you have moments here, 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 slope deflection is very happy. That's what it's designed for. That's how it works. But in here, when the load's coming on this one, it's not happy. So what we do, we transfer that equivalent load into the fixed end moments format. OK, so what we are doing here, 60 kilonewtons goes on left side and right side. We just distribute it to make the slope deflection method happy. All the displacement methods are in that sense. They don't like something, the load coming onto that members. So, and then we go in our lecture notes, and you don't need to remember that. We will give you the tables. In case in your assignments, if you can't find this one, you Google it. There are heaps of fixed end moments equations are there. OK, so if you say that my assignment has a loading which is not covered here, just find it from the Google, that fixed end moments, and it will come like thousands. All right, so now we are in this case probably. Let's grade the whole things. All right, so we just compare. So I think this is the case for this one. So fixed end moments of AB. By the way, clockwise is positive in the displacement methods. All displacement method clockwise is positive. So fixed end moments AB equation is given here. PL on 8. And this one is anti-clockwise. You can look at this is minus P is 60 kilonewtons. Length is 4 meters over 8. It gives you minus 30 kilonewton meters. What is fixed end moments? It's just the presentation of 60 kilonewtons at the node. OK, that's we just transferred. And fixed end moments of BA is in here, and that is clockwise, so it's positive. PL on 8, positive 60 kilonewtons times by 4 meters over 8, positive 30 kilonewton meters. So far so good. It's fully up. OK, that's the maximum. All right, any questions there? Finding the fixed end moments. You can find the fixed end moments for any case that is given in your assignment. Just break it down. All right, fixed end moment BC. Which one we should take? We should take this one, I think. One side fixed, another side roller, 20 kilonewtons. This one is anti-clockwise. So fixed end moments of BC equal to minus WL square on 8. No problem. So minus WL square over 8. Right? Can you see it? All right. So WL square minus, because it's anti-clockwise, W is 20 kilonewton per meters. Let's write 20 kilonewton per meters times by length 4 meters square over 8 is give you minus 40 kilonewton meters. Right? So we find AB, BA, BC, fixed end moments. And those fixed end moments are just the presenting all internal loading onto the nodes. Now, second, we're going to write the slope deflection equations. There are only two equations. There are two possibilities. Where they are, I can show it to you. If you go in the lecture notes, the one is here, and I will tell you how to use them. One is here. And second one here. There are only two equations that you need to dealing with. All right, I will redraw this figure again for you. A, B, 60 kilonewtons, 2 meters, 2 meters. B, C, UDL load of 20 kilonewton per meters, and that is two cases are given here, and that has a length of 4 meters. Let me put this 4 EI, by the way, and that will have a 2 EI. That is the flexural rigidity that is given in the questions. Right. Now, these first equations are used when your far node is fixed. So every member, that's let's say member AB, has a two equations. MAB equal to. So in MAB, A is a near node. A is a near node or near joint, and B is a far node. You always look the far nodes. You always look for the far nodes. The far node is fixed. You can look at that. Far node is fixed. So if the far node is fixed, you can use these equations. If the far node is pin or rollers, you can use the second equation. That's the only difference. You look at the far node always. So if I want to calculate moment at AB, then A is the near node, B is the far node. In that equations, B is the fixed supports. All the internal supports are fixed, as I said. So let's write it that one. 2 EI on LAB to near node theta A, far node theta B. That is the element over length L plus fixed end moments of AB. I just use these equations to write it in the form of MAB. You can stop me if you don't understand that. Right, in that case, 2 EI is 2 EI because it's given here in the questions. Over length is 4 meters times theta A. Look at that. If I draw the loading, the slope is 0 here. You have a slope here, and you will have a slope here. So theta A is 0 because it's a fixed support. The point A cannot go horizontally, cannot go vertically, cannot go in X, cannot go in Y, and it cannot rotate. So theta A is 0, theta B is not 0, theta C is not 0. So theta A is 0. Let's substitute that. Theta A is 0, theta B is there. We need to find. There is no settlement. Support is not settling. It's not given in our question. Support B, support A, or support C is not settlement. So delta is 0. Length 4 meters. Fixed end moments of AB. We found minus 30 kilonewtons. Minus 30 kilonewton meters. In that case, this cancels. This cancels. You have EI. This all gone. Theta B minus 30 MAB. Let's put that as an equation number 1. You can stop me if you don't understand any of the parameters or any equations and how we do it. So then that's the moment at joint A. Similarly, let's do the MBA. Let's write the equation. Look at the far node A. Now the far node is A. When I say MBA, far node is A, and far node is fixed, so we can use these equations. So this equation again, let me write it down. Length of BA, 2, near node is B, far node is A, 3 times delta on L plus fixed end moment of BA. Right? So we write in terms of BA, where B is a near node, A is a far node. And we just use these equations. Let me put close to here so you can see. Same configurations. 2 EI for member AB is 2 EI. Length is 4 meters. Theta B we need to find. Theta A is 0. No settlement. Length is 4 meter. Fixed end moment 30 kilonewton meters for BA. We calculated that one from here. Right? So this would go on. So 2 EI theta B plus 30. Yes, please. Okay. Yes, please. Go ahead. Sorry, which one?
When you say settlement,
Yeah, so
just the displacement of that.
you know these soil mechanics, GTD and all. You do this soil stuff. Sometimes the soils are not strong enough. You learn those things.
So they're different things.
So sometimes in the structures, you may find after the period of time, you may find settlements. Let's say you are an engineer and you got a job saying there is a 30 years old property. This is the initial soil reports and all, but after 30 years, it's just go down 5 millimeters down. Possible. It's settled. So in that calculations, you might need to include that settlement. So in these examples, settlement has not given. So therefore, we take delta equal to 0. In lectures, there is one examples where there was a settlement, where we have demonstrated delta. If you substitute delta here, that is not a big issue. You can just have a delta here, theta B plus some value.
So it's not the same as displacement.
It's not a displacement. It's not a delta is not a displacement. It's a settlement. And I explain. Yes, please.
Can you just explain the MI positive 30 for the FEMPA?
Clockwise, positive.
So it doesn't go up the diagram.
Which diagrams?
Because that diagram says that.
Which diagram?
So the B on the arrow.
B.
Yeah. Yeah, it'll be fine. I'll figure it out.
No, don't need to figure it out. Okay. You understand these figures?
Yep.
This arrow.
Yep.
What is this one? Which direction?
Counterclockwise.
Counterclockwise. Counterclockwise, negative. What is this direction?
Clockwise.
Clockwise, positive. What is this direction?
Right. So we're not, just because on the diagram,
On the diagram, yes.
it doesn't have a negative or a positive, but the arrows
Yeah.
are going in different directions. You disregard that.
This arrow,
Yep.
they are not saying is it positive or minus, because this table is very general. This is our assumptions at the start, saying all the moments would be clockwise. Now you may ask, how about I assume counterclockwise positive? I never try whether it's counterclockwise positive works or not. But in displacement methods overall around the world in these books and all, they just use the clockwise positive to have it all. Okay, does it answer your question? So these tables will not going to tell you whether you take it positive or negative. You draw it, and then these tables only used to get the equation. The equation meaning PL over 8 or this or this. Don't worry about the positive and negative. You see your diagram to get the positive and negative and get the equation from here. Okay. Anything else? All right, so all good. So far so good. So we got B, and then last one is these diagrams here. MBC. So let me write MBC. Now C is a pin or roller. You can look at that. C is a flat node, pin or roller. So we need to use these equations. Now, not the first one. As I mentioned, you always look for the far nodes, whether it's very easy to see. Okay, it's nothing complicated. So we're going to use these equations now. So 3 EI on LBC theta B minus delta on L plus fixed end moment of BC. So 3 EI is given different. In our examples, 4 EI. So 4 EI. Length of BC is 4 meters. Theta B we need to find. That is 0. Fixed end moments of BC is minus 40. So here this 4 gone. 3 EI theta B minus 40 MBC. Right. Now step number 3, equilibrium. Now look at this one. What we done here in this diagram, A is theta A equal to 0. There is no problems. We disturb B. We just done something wrong with B. What we done B wrong? That we put these moments here. We put the moment here because we don't want 60 kilonewton here, 20 kilonewton here, and we done some changes at B. Right? So we need to make sure that whatever the moments comes at B should be in equilibrium, because some of the moment at point B equal to 0. Right? We want to make sure that whatever the moment transfer from here or here should be sum them equal to 0. If it's not that equal to 0, we need to making sure we put extra moments there. So equilibrium at B, not A or not C. We just have to equilibrium at B. Like in the force method, we have compatibility conditions. Here in the displacement methods, we have equilibrium conditions. So equilibrium at B, sum of the moment at B equal to 0. So look at the diagrams. In the diagrams, we have a moment MAB, moment BA and moment BC. Right? So we will just take moment BA plus moment BC equal to 0. All the moments coming at that joint should be equal to 0. You agree with me? Because that joint is not in the space. It's not rotating. It's not a skateboard. It's staying there, meaning all the forces on B equal to 0. All the moments at point B equal to 0. Point B is not rotating. So let's substitute the value. MBA we found here. 2 EI theta B plus 30. 2 EI theta B plus 30. Plus, yes, please, sorry.
The direction of the marble.
Not really. We just sum them up as it is. With theta B might get positive or negatives, but just sum them up. And then 3 and 5 EI theta B minus 10 equal to 0. So theta B equal to 10 on 5 EI. So theta B is equal to 2 on EI. Right? That's our ultimate goal here, to find the theta B. Right? That is a displacement matters. We need to find the unknown displacement. The slope is the displacements, part of displacement. So we find unknown displacements. When you find the unknown displacements, the step number 4, we find the n moments. How do we find the n moments? Let's write equation 1 again. What was the equation 1? EI theta b minus 30. EI theta b minus 30, less of the value. All right, MAB done. MBA, let's write equation number 2. Equation number 2, 2 EI theta b plus 30. 2 EI theta b plus 30. 2 EI, 2 on EI theta b, 34 kilonewton meters. Equation number 3, MBC, 3 EI theta b minus 40. Now you can stop here. As I mentioned, I give you several stop buttons, so you can stop and check whether the calculations are going or right or wrong. Look at here, minus 30, positive 30, because this moment is MBA at the joint B and MBC at joint B, equal and opposite. If you get wrong, this number is different, then you need to go back and check. Yes, please.
Why, could you explain why we pick point B?
For the equilibrium?
Yeah.
Yes, because look at that. That is called in the lectures, I think, let me actually, in the force methods, we done static indeterminacy. Static indeterminacy. Here we need to do the kinematic indeterminacy. Kinematic indeterminacy, that is called degree of freedoms. Degree of freedoms meaning, degree of freedoms here is joint A is 0, because there are 3 degrees of freedom in 2D plane. 3 degree of freedom meaning the joint A can have a degree of freedom in X direction, degree of freedom in Y direction, and third degree of freedom is rotation. There are 3 degrees of freedoms which every joint has. You always look at the joint in the force methods. Displacement methods in here. So look at the joint number A. How many degree of freedom? There are 0 degree of freedoms. The joint A is fully fixed. There is nothing else that will go. Now point B comes here. Point B. Point B has a. It cannot go in the X direction because beam, we neglect axial deformation in the beam. That is our initial assumption. So this one don't count. Vertically it cannot go, but this joint B can rotate, right? Because this roller, so it can rotate. So it has one free degree of freedom. It can free in the one direction, which is rotation. So it has a. So this beam has a static kinematic indeterminacy 1. So therefore we have one equilibrium equations, and that one equilibrium equations comes here for the joint B to be in equilibrium. Therefore so you need to scan your whole beam.
Could you do that same thing with C then?
Yeah, no, C you cannot do it because you don't have any continuous beam.
Okay, so you need to continue both.
You need to have a continuous both sides. If you have a C and you have more D, then you have 2 equilibrium equations. We have next questions coming for that too. Does it answer your question? I think that we covered in the lecture. I cannot see you in the lectures probably. Yes. So you watch it? No, reading it will not help. All right. So, but does it make sense? Yeah. So static indeterminacy in the force method, kinematic indeterminacy in the displacement method, and here kinematic indeterminacy at point B. And the number of kinematic indeterminacy tell us number of equilibrium equations. What is the static indeterminacy in here? Like last week, capital D. You remember that or not really? Last week we done static degree of indeterminacy, which is number of unknown forces minus the equilibrium equation. How many forces are unknown? 3 4 and 5. 5 take away 3, 2. 2 static degree of predeterminacy. That is in force method. In displacement methods, we use kinematic degree of indeterminacy. That kinematic degree of indeterminacy, just you look at the joints. It's all about the joints here in the displacement methods. Okay. All right. So we done so far what? We find all the moments and look at this one. Now let me put that one in the diagrams. Okay, so here positive is clockwise, I believe. We still follow the same thing. Minus 28 negative. So 28 kilonewton meters. I did not put negative, I just put the arrow, and that is MAB. And then you have clockwise AMBA, and that is positive 34 kilonewton meters. And here you have MBC 34 kilonewton meters anti-clockwise. All right. So far, so good. All right. Now let's break it down again. That you have this joint number A, joint number B. It has a moment of 28 kilonewton meters. It has a moment of 34 kilonewton meters, and it has a 4 meters here, and it has a loading of 60 kilonewtons with the 2 meters each side. And let's say there are shear forces or reaction forces, let's say AY and let's say BY on the left side. So let's say, and then you can break it down to another one here, that let's say BY on the right side. Let's say this is B, and you have 34 kilonewton meters, UDL load of 20 kilonewton per meters, and then you have a 4 CY, and that is 4 meters. Do you understand what I done? I just break the whole things, put the moments that we found, and we have unknown reaction forces. That is our steps now. All right, now let's take the moment at point A equal to 0 anti-clockwise, clockwise positive. Let's keep it clockwise positive for that case to be happy. 34 kilonewton meters minus BYL times 4 meters plus 60 kilonewton meter 2 meters minus 28 kilonewton meters equal to 0. Check on my shoulders if I'm making any wrong or anything I forget. Just check it, please. 120 minus 28 BYL equal to 126 on 4, 31.5. That is BYL. Sum of the force in the y direction upward is positive. AY going up, 60 kilonewton coming down. BYL is going up. You get AY equal to 28.5 kilonewtons. Right? You know this story, this one. You done it by this time 50 times. This statics equilibrium now. We have all the forces that is known to us now, so we can use the equilibrium to solve the reaction forces. We can use the same style here in the BC. Sum of the moment at B equal to 0. Anti-clockwise is positive. CY times 4. Oh, sorry, make it clockwise positive. Minus CY times 4 meters plus 20 kilonewton meters times by 4 meters times by 2 meters plus minus 34 kilonewton meters equal to 0. So CY equal to 31.5 kilonewtons. Sum of the force in the y direction upward is positive, 31.5 kilonewton going up. BYR is going up, plus 80 kilonewtons coming down, equal to 0. So we got all the values now. AY 28.5 kilonewtons. BY, we need to sum them up both left side and right side, 31.5 and 48.5. 31.5 plus 48.5. Yep, 80. So 80 kilonewtons at B. A, B, and CY 31.5 kilonewtons. UDL load of 20 kilonewton per meters. That is 60 kilonewtons. And there is a reaction moments here, which is 28 kilonewton meters. Ooh. Let me fix up that one. All right. So now we have put all the moments there. Now we just need to draw the shear force diagram and bending moment diagrams. 28.5 going up kilonewtons. Then you come across 28.5 take away 60 will give you 31.5. Go across 31.5. This is minus plus 80 will give you 48.5. And then you will have these 31.5. You can join them. Right? That is shear force diagram, SFD in kilonewtons. Bending moment diagrams. You can start with 28. Then you can go up to 29. You know these rules. 28.5 times by 2 meters, I think. So 28.5 times 2 will give you 57. So 28 take away 57 will give you 29, or 57 take away 57, 29. And then from 29, you can come down. There are 31.5. This one. So this one would be 31.5 times 2. You get 63. 29 take away 63, get 34 minus. You get 34 minus. And then from there, you can just have it parabola with the peak point in the points where you get this. And if you want to know these values, you can just need to find this x distance. X distance, you can calculate y is equal to mx plus c. So I think y is equal to what was this one? 20 minus 20x plus 48.5. So if I want to find that, so 48.5 divided by 20, you get 2.43. And then you will have how much? 4 take away 1.575. 1.575 meters. So then you can just have it half times 1.57 times 31.5 will give me this distance 24.81 BMD kilonewton meters. Which one not understand? Any value that is possible. This number, this number, this number is anywhere. Or everything is does not make sense. I can go over it slowly if you like. All good?
The numbers space gas give for the reaction forces is very slightly different that why if we just do it?
Because of the rounding numbers that we use here in the space gas. Sorry, rounding numbers that we use in the mathematics.
Yeah.
This is slope deflection matters. Space gas is stiffness matters. Week 11, we will teach you how the space gas do the calculation behind the screen.
Okay.
But slight difference coming from two reasons. Rounding errors coming from our calculations. We take 2 decimal places, 3 decimal places, and slope deflection matter itself. All right, anything else? Any questions there? I think no questions. Then in that case, we move on to the next one. There are slight changes there. Copy. Paste. So, tree span beam. Throw the SFD and BMD for EI equal to constant. So, step number 1, fixed end moments. We don't touch A, but B we fix it with 60 kilonewtons, 2 meters on each side. Fixed end moments of AB, fixed end moments of BC. B fix, C internal fix, 50 kilonewtons meters. Fixed end moments of BC, fixed end moment of CB. CD roller 10 kilonewton meters. We can't touch D. Look in the exams, you don't need to draw this one, okay? Think. This is just for me to explain you. Just straight override the fixed end moments equations. You know what I mean? Don't waste your time because these diagrams is just for you, for me to explain you. Once you get the practice, you don't need to, like in the solutions, you don't need to write, you don't need to draw these fixed end moments diagrams, right? You can just straight away jump on the equations, right? The equations from the tables. So, fixed end moments of AB, clockwise is positive here. This is anti-clockwise. I think from last examples we had done PL over 8. So minus 60 times 4 over 8 minus 30 kilonewton meters. Fixed end moments of BA, positive PL on 8 clockwise, 60 times 4 on 8, positive 30 kilonewton meters. Fixed end moments of BC. Can you please find? I think those will not be correct. This will go this way. This will go this way. Can you please find from your Google friend that if they can give us these fixed end moments, because in our lecture notes, this case is not given. So this is an exercise for you in the assignment in case if there is any case coming that you don't able to just say fixed end moments beams and then it should show some things. So can you please find the value for me, the direction as well, fixed end moments at BC 50 kilonewton meters. And tell me, in the solution it has a value, but I just want you to take a reference from somewhere. Does it have somewhere? M04. Does it show somewhere clearly with the direction as well? Yeah, so the direction both are going clockwise. Is it correct? Same like in my figure. Right. So keep in note that you have a. Does everyone got it? Something somewhere? This one here. Yeah, so this is looks more close what happens here? This one is not in the center. There, we are in the center, I believe. We are in the center. This is in center, and by 4, both are going clockwise. Do you agree with me? Right? Raise your hand if you can't find the you can't find something. This one here looks this one. No, this case is A and B. Then if you substitute A equal to B, that will give you this value. But I think that they found some more similar case. Yes.
Why is it going?
Yeah, because you can look at this. If you have an M going here, you need to have those reaction moments, or what you can say that for equilibrium of these members, you need to have this. Because you can see this one going which way? Anti-clockwise. So here they should be, because all those joints, they are in the equilibrium. These all the members are also in the equilibrium. You can see that 50 kilonewtons. To have these 50 kilonewtons, we need to have these clockwise moments going on those.
Aren't they all going clockwise?
This one. Oh, sorry. They are all going clockwise.
Yeah.
All right. So let me help you. Yeah. So. Yeah. So. All right. So in our theories, okay, let me explain. In our theory, what is those peaks and moments? Those peaks and moments are representation of 50 kilonewton meters. Right? So in our theory saying that we don't need 60 kilonewtons, we don't need the 60 kilonewtons on the members. So we don't need these 50 kilonewtons on the members. Right? That's what the theory says. So if the 50 kilonewtons is here, some will goes here, some will goes here.
And they become anti-clockwise to sort
Anti-clockwise to sort of.
if the whole has been
Yes.
wouldn't be able to have to
No, the equilibrium, I think I just misinterpreted the equilibrium things. I think equilibrium comes this one later. We will make sure that equilibrium is not violent. We will make sure that all the moments and all the forces and everything will be equilibrium at the end. But right now, what we have done, we disturb the whole beam by distributing all the internal forces to the joints. And when we distribute it, then we will check the equilibrium at the joints before we calculate the final our calculation, making sure that our joints are equal. So right now we are disturbing all the joints. How we disturb it? Because we are transferring all the internal forces onto the joints. That is the slope deflection method. As I mentioned, slope deflection method does not like any forces coming onto that member and to the member. So we are transferring those to the joints through the peaks and moments. Does it make sense? And you might say that, okay, equilibrium. Yes, equilibrium we will check. That they should be in equilibrium when it comes to the transpose. Okay. Does it answer your questions? So 50 kilonewtons clockwise. If it is going anti-clockwise, do you have tampons which are going anti-clockwise? No.
Like we could just say that, the FEM, the PT, and slip, the FEM. That's what makes it. I forgot the name.
Does that make sense to you?
Yes, one more.
So when we do the equilibrium equation, when we're doing it for that section, don't we say
So these sections you say that is not in right now in the equilibrium. That's what you said. Section BC is not in equilibrium. And I agree with you. They are not in equilibrium. We purposefully make that in equilibrium.
actually they would be? Because if we're looking at joint, let's say
They won't be in equilibrium until we do the moment equations, not the fixed end moment.
Yeah, the fixed end moments are are not. What is fixed end moment? Fixed end moments are not supposed to deal with equilibrium. Fixed end moments are the presentation of all the internal loading to the joint without.
What do you base the direction of the moment on then? For that being, so how did you know that it'll be going clockwise on the left hand side and then anti-clockwise on the.
So you mean, so when you come here, how do we know that this is going this way and this is going this way?
Yeah,
That's
it.
compared to, okay. So if you have a moments, if you take a moments here, right? So if you, let's say 60 times 2, I think I need to do more investigation on fixed end moments and see how they derive these equations. Let me come back to you, because there are other methods that because these tables that we just give it to you.
I think I sort of get it, but I don't think the way I'm thinking.
Yes, what are you thinking?
I have to draw. I was thinking.
Let's have to keep the discussion at end. Okay, you just stay with me later on. All right, so you found these cases where you have these 50 kilonewton meters and moments and so on. So in that case, you have m/4, and that m/4 is clockwise. So we take it m/4 positive, 50 on 4. So that is 50 on 4. You get 12.5 kilonewton meter positive. Fixed end moments of CB, m/4, 50 on 4, 12.5 kilonewton meters, and fixed end moments of CD equal to, this case is given in our
Would you get if you put base the other way?
yes, CD, sorry, which one?
You know how you do the arrow up? If you do the arrow down with the hand, it'll be
CB, yes, which one?
basic. Could you do just that one up?
This way?
Yeah. How you draw it down? Would you do it to negative? And
No, it's not like have you seen that table?
confusing.
It's confusing what is happening here. No, this is not the right one, because you have this one going in this direction. I think they found the tables which is yeah, these are here, but they do not put arrows. There are heaps of them, but some are not. They just. This is our tables. This is from our book. How about here? There are heaps of them. Oh, there you go. Yeah. Right. Fixed moments at CD, and that is anti-clockwise. So we will have a WL square over 8 minus WL square over 8, and that will give you minus 10 times 4 square over 8, which gives you minus 20 kilonewton meters. Now we write the slope deflection equations. Second, now the MAB far node is fixed, so we can write and all EI is constant. So 2 EI on length of AB is 4 meters, theta A plus 2 theta A, theta B, that is no settlement, fixed end moments of AB minus 30. Theta A is 0 fixed, so EI on 2, theta B minus 30. MAB, equation number 1. MBA, 2EI on 4, 2 theta B plus theta A minus 0 plus 30. Theta A is 0. 2 to 4 cancels. EI theta B plus 30. MBA is 2. MBC, both are fixed, B and C. So 2EI, length of BC is 4 meters. 2 theta B plus theta C minus 0 and plus 12.5 MBC. So that will give you EI on 2 theta B plus theta C plus 12.5. So EI theta B plus EI on 2 theta C plus 12.5 MBC. MCB equal to 2 EI on 4, 2 theta C plus theta B minus 0 plus 12.5. So EI on 2 theta C plus theta B plus 12.5. So EI theta C plus EI on 2 theta B plus 12.5. Are you following me, or is too fast? Just stop here. So MCB is done, and the last one is MCD, but we need to use another equations for that, because MCD equal to, what was the another equations there? 3 EI on L theta C and take 0 plus MC fixed and moment CD, which is 20. It's 20. So 3 EI on 4 theta C minus 20. That will be your equations. Let's write the equation 2, equation number 3, equation number 4, equation number 3, equation number 4, and equation number 5. Right? Now we have to have a number 3 equilibrium at B and C. So at B we have moment which is MBA MBC. MBA plus MBC equal to 0. Now MBA we found EI theta B plus 30. EI theta B plus 30 plus MBC we found EI theta B plus EI on 2 theta C. EI theta B plus EI on 2 theta C and plus 12.5 equal to 0. Right, so if I collect the like terms, 2 EI theta B plus 0.5 EI theta C plus 42.5 equal to 0. Let's say this is equation number 6. Let me write in that format. EI theta B plus 0.5 EI theta C equal to minus 42.5. Let's write this equation number 6. And then at C we have a CB and CD. CB and CD. So CB is equal to EI theta C plus EI on 2 theta B. EI theta C plus EI on 2 theta B and plus 12.5 plus MCD. EI 3 EI on 4 theta C. 3 EI on 4 theta C minus 20. All right, so 0.75, so 1.75 EI theta C. Let's write the theta B plus 0.5 EI theta B plus 1.75 EI theta C and then 12.5 7.5, so positive 7.5, equation number 7. So we have two simultaneous equations now that need to be solved to calculate theta B and theta C. And if I use this theta B theta C 2.5 0.5 1.75 minus 42.5 and 7.5. So we can do the inverse. So 2 times 1.75 take away Yes, which one? That is simultaneous equation. I think grade, I'm not sure, grade 7, grade 8. I can go through it. All right, let's do it from here.
I get the matrix, I get up to the,
So-
I got 6 and 7 after
You-
the matrix right? And matrix I do not
You,
remember how to
you,
solve
you
it.
understand this one?
You've got that, but don't
Yeah.
know how to solve it after that.
So after that, you need to find determinant that. Difficult. So you multiply diagonal 2 times 175, take away this one. Do you understand that?
Just wondering to myself.
Okay. Then you swap these mean diagonals and then put minus in front of those diagonals. Anyway, this is correct or I forget? Then you just have this as it is. And then one that, and then you just put this and you do across down. 1.75 times this one plus this times this. Across down. You understand?
I remember that. I remember that. Bit,
You remember that? Okay. Fix a moment. I'm still thinking. So after this one, I have some answers. Which part not understand? Any questions?
The matrices, I don't remember that whole, just use that really. I do remember.
Maybe in the school they teach differently. In school, they may have different methods.
Yeah,
Have you done the 2 by 2 inverse matrix?
that's why I just
Yes.
forgotten it.
Okay. All your metrics will come together in week 11. These are all matrix method. That's the name of the even stiffness method or matrix method. Everything. Because computer likes matrix. They don't, if you want to computerize the slope deflection matrix, not possible. I'm not sure. I may be wrong. I don't know. Maybe some, but there is something going in this direction. Maybe this diagonal swap other way or this minus. You just check it.
Slightly different.
It's got
Yeah, maybe something plus or minus. Which one?
one.
This one?
1.75 take 42 point.
Not take, multiply.
Yeah, the time there.
Yes, and then you need to do this one as well.
Take 0.7. Yes, negative 78.1.
Yep, negative
That's what I
7.
get.
Yes, so that should be fine. Negative 70,
I get
negative 78.125,
125.
and then this is better. Well, I can help you to, if you have not done it. Well, there is another way to solve a simultaneous equation as well, you know. Yeah, you can make a one subject and you put it in the another one and so on. Right?
Hmm.
There is another method to solve the simultaneous equation as well. You don't need to use matrix. You can make that whole equations as a one subject. Let's say in this equation you make theta c equal to something and you sub back into the another equation, find, you know that.
Yeah.
All right, let me so this is simple two equations. Can you solve x and y?
Yeah.
That's the same thing that we done, right? But it was EI and theta b and theta c looks like more trickier. If you have this 2x plus 3y equal to 5, 5x plus 7y equal to 10, and say the question is what is x and what is y? Meaning that what value of x you put here, what value of y put here, that will give you the answer 5. What value of x you put here, similarly, what value of y you put here, your answer get 10.
Yeah.
When you are school, you might think, where are we going to use this all stuff? Here is the real applications. Okay. All right. So finding the slopes in the beam. So now we're going to substitute back those values into our equations. MAB equal to 0.5 EI theta B minus 30 equal to 0.5 EI minus 24 on EI minus 30 equal to minus 42. MBA EI theta B plus 30 EI 24 on EI plus 30. So you got minus, so you got 6 kilonewton meters. MBC EI theta B plus 0.5 EI theta C plus 12.5. So EI minus 24 on EI plus 0.5 EI 11.15 on EI plus 12.5. Minus 5.93 kilonewton meters. MCB 0.5 EI theta B plus EI theta C 12.5. So 0.5 EI minus 24 on EI plus EI 11.15 on EI plus 12.5. 11.63. 0.5 times minus 24 plus 11.15 plus 12.5. 11.65 kilonewton meters. Oh, we stop here. Forget to stop. 6 and this one matching, right? Don't 5 minus 5.93 is rounding error as I mentioned, and 6. So I stop here. In these steps, I also recommend you to stop because as you know, this is long way coming all the way here, and there is a few more steps to go. So you want to stop and make sure that these numbers are matching, plus and minus. If it's not matching, you quickly go back and check it. Okay. So as I mentioned, in these subjects, your answer will not never go wrong. Okay. There are multiple ways to do those checks. So MCB done. MCD equal to 0.75 EI theta C minus 20. So minus 0.75 EI theta C is 11.15 on EI minus 20. Oh, that is just a plus. (11.63 kilonewton meters). Again, quickly check that. That is 64. So that is again check. These numbers are matching with plus and minus. Okay. Now, once you find these values, we need to find those reaction forces. Let me draw this beam again, whole beam. All right. AY, BY left side, 60 kilonewtons, 2 meters, 2 meters. AB, we got minus 42. So 42 kilonewton meters. Clockwise, anti-clockwise, sorry. And then you have this one, which is MBA 6 kilonewton meters. Clockwise. This is point A, point B. BY right side, CY left side, moment 50 kilonewton meters, 2 meters, 2 meters. At MBC minus 5.93. We don't put minus. In MCB 11.65. And the last one, that MCYR dy 10 kilonewton per meters, 4 meters. And this one, last one is 11.64 kilonewton meters. Right? Yes, please.
Yeah, it corrected itself to go in anti-clockwise.
Yes, it corrected itself
So
to going.
if we had assumed, let's say, is it okay to assume the direction of the moment at the start?
Well, I don't know. I need to check.
Okay.
Yeah, I can't confirm it. Yeah, but for your, yeah, look at this one. That's you say that this one going here, this one going here, this one going here. Everything in equilibrium looks like it. Right? So it's just give you the negative answer here. That will just you forced to put in this direction. But I think I will come back to you, as I mentioned, after these examples. I will talk about fixed end moments. That we do it together. There is an exercise there. I will do it as well. You do it as well. We both compared our questions.
I understand how it works. I just don't understand how we pick those moments.
Well, those are coming from tables.
Okay.
And I don't know not explain you how these tables someone generated. Someone smart like you who has very good understanding. He has done the table, and we just use the tables without where this coming from. You know, we should have understanding at least one or two case how they come up with those numbers and signs. So after this one, I will give you an examples. I will also do it, and next week we will check it. That let's take one case from the tables, and we find ourselves and see. Okay. That will give us the understanding and unpack that tables. All right. So far so good. Then here, how you put those thing values and all. And these ones you done it 25, 50 times so far now. That you just take a moment at point A and you find BYL, then you put some of the forces in Y direction, you find AY. Just repetition. Right? So let's do that. Sum of the moment at A equal to 0, let's keep it clockwise positive throughout the example. 60 kilonewtons times by 2 meters minus 42 kilonewton meters plus 6 kilonewton meters minus BYL times 4 meters equal to 0. BYL 84 on 4. (21 kilonewtons). Sum of the forces in Y direction upward is positive, 21 going up minus 60 kilonewton down plus AY equal to 0. AY equal to 39 kilonewtons. Plus rounding it up. Sum of the moment at B equal to 0, clockwise is positive. 11.65 plus 50 kilonewton meters minus 5.93 kilonewton meters minus CYL times by 4 meters equal to 0. (13.93 kilonewtons). Sum of the force in the Y direction. So BYR would be minus 13.93 kilonewtons. Two more to go. Sum of the moment at C equal to 0. Clockwise positive. Minus dy times 4 meter plus 10 kilonewton per meters times 4 meters minus 11.64. meters, and then we need to multiply by 2 meters here as well. So 10 times 4 times 2. I think we got everything now. AY 39 kilonewtons. 60 kilonewtons here. 2 meters, 2 meters. BY, we need to sum them up. BY left 21 and minus 31. 21 minus 13.93. You get 7.07 kilonewtons BY. CY, you get again two values, 13.93 plus CY right. Did we find CY right? CY left, dy. Where is CY right? Oh, CY right, we did not find it yet. So let's me do this one. 17.09 going up. Take 40, yep. Take 40 plus CYR equal to 0. So CYR equal to 22.91. So that is 22.91. 36.84. dy 17.09 kilonewtons. C D UDL load of 10 kilonewton per meters. 4 meters. 50 kilonewton meters. 2 meters. 2 meters. The moment here would be MAB. Let me find the value for MAB. MAB minus 42. So it goes this way. $42 kilonewton meters. All right, so you have all the reaction force, reaction moments. Now we can draw the shear force diagram first, and then we draw the bending moment diagrams. 39 going up, then 60 down. 39 take away 60 down, 21. 21 here. Going across, 21 take away 7.07, 13.93. Going across, that is 13.93. Take away 36.84, 22.91. And 17.09. Right, bending moment diagram, SFD in kilonewtons, 2.36. So now we have 42.2, 42, and then you will have this value of 39 times 2, 78, 42 take away 78, or 78 take away 42 and give you 36. So you got 36 here. Then this value here, 21 times 2, 42. So 36 take 42, give you 6. And then you have another one here, 13.93 times by 4, 55.72. Oh yes, we have 50 there. So we need to take into account that one as well. So let me think. Yes, that's right. So let's do this one, 2 meters first. So here 13.93 times by 2. You okay with me? 13.93 times 2 is 27.8. 86, and then you plus 6 with that, so you get 33.8. You continue that line up to 2 meters, and that give you 33.86, and then you have 50, so 16.14, and then back to this guys, which is 27.87. So 16.14, 11.78, and this guy's here. Now, if you want to find this one, y is equal to, what is the slope? Slope is 10 x plus 22.91. So 22.91 divided by 10, which is 2.291. And then you take away 4. 4 take away 2.291. 1.709. So this value would be 1/2 times 1.707 times by 17.09. To 14.62 kilonewton meters. I know it's long and it's fast because I am running out of the time. But I think you done this on week 2, week 3. We revised plenty times these kind of examples. So therefore, I just, but you let me know if anything that's these numbers, where these numbers comes from. I can help you. Yeah, frame 1, we need to take it 1 frame at least. Now for fixed and moments, I will do this example as well. If you can do this one example with me as well. Let's say you have, let's take this one, okay? Let's say someone give you this one, 60 kilonewtons. Let me write neatly. Let's say we have 2 examples that we want to solve. You have a 1 beam. Forget about this. You have, you have 1 beam, and that beam has a 60 kilonewton coming, and it is in the 2 meters. Now our question is, we don't know the directions. Okay, we don't know the direction, moments coming here or there. We don't know these directions. Let's assume these are, let's say this going this way, let's going this way, and this one coming this way. Our question is to find these moments. Is it possible to solve? So far we teach you this one. Forget about fixed moments, anything. There is a one example for you. That there is a beam 4 meters long. This beam has a concentric force 60 kilonewtons coming in the middle. Question is asked, what would be the reaction moments here and here? Is it possible to solve? You know what I mean? You have a beam, forget everything that we are teaching slope difference, just these standalone examples. That you have a beam which is 4 meters long, 60 kilonewton coming. What would be the reaction that is coming here? Possible to solve?
Make an assumption that there's no axial.
Let's make an assumption. This axial force are 0.
Then it's going to be 30 kilonewtons up on each support. Requirements would be.
Yeah. So yes, we need to solve. There is a force methods. Degree of indeterminacy is how much? On let's say axial is not there. 1, 2, force 2 unknown. 4 take away 2. Degree of indeterminacy is 2. We can solve, right? We can remove this support. We make it this one, and we remove these supports. Apply the load, find the displacements, and put this reaction force up, and so on. Right?
Yep.
So the question is here. Let's solve this example by ourselves, and then we compare our answers with the table. Okay, I will solve as well, and I'll give you the solutions in the And then second examples that we're going to take it in the same natures, that let's say we have a same beam 4 meter long, but instead of 60, it has 50 kilonewton meters. We don't know the direction, let's say, put any directions, we assume any directions and calculate those moments. Possible? We teach you that one, right? Because if you go and after 1 year you go on this one, and I have many students sitting in the office say that, okay, you coming from structural analysis, okay, this is an example, can you find the reaction force? You understand, because fixed supports are everywhere. It's not that I just throw it. It's the fixed supports here. Reaction force we need to find 60 kilonewton coming 4 meter long. There is no 60 kilonewton. Let's say 50 kilonewton meters. Sorry, this one 50 kilonewton meters. Moments coming in the middle instead of 60. I change that. Okay, there is not 60, only 50. Say deep 2 meters, 2 meters, 4 meters. Let's find the moments. And that will unpack the table that we are using blindly. Right? We close our eyes and take this one. Okay, so that will unpack. That one I will solve as well. I have not done this unpacking business, so it will helpful for next year to teach the students. 15 minutes. Let's do the one examples. Hopefully these small ones. I think this tiny one looks good. So let's do that one. These are frames, because these methods can be used in the beams and this can be used in the frames. What is the difference between beam and frame? Looks different. That's the one thing. But let's say this is my beam. Sorry, I just let's say A, B, and C. Let's say some kind of a loading coming on here, and you have a frame. A, B, and C. Let's say you have this AB. And here you have B, C. What is the difference with both are? I grab this part from beam. I grab this part from frame. The fundamental question is, they are both looks horizontal. What is the difference between beam and frame elements? This is beam elements. This is beam. I grab it from beam. This is frame elements. You understand the questions?
Break down like that, there is no difference.
When you break down this one, still there is a difference. Look, here note axial deformation. This guy P2 will going to push this point B. You have axial deformations in here. In the sense that beam elements has vertical and moments. But in here, you have vertical, you have moments, and you have this one. That's the difference. In frames, you have these axial forces. You can't ignore that, because frames is structures in a way, and their force are, look at this P2. I intentionally put that one. This P2 going to put the axial forces here. So that's the fundamental difference between the beam and frame. That in the frame, you will take into account those axial deformations, unlike we ignore in the beam. All right, let's start now. All right, so next week, fixed end moments, I will clear it up, okay, with those two examples. And if you have to give it to go, you can try. All right. Here is the questions. Is a fix at A, pin at C. We have point B. And this is 32 kilonewton per meters. We have 16 kilonewton, and we have 2 meters, 1.45 EI and EI, right? And this is 3 meters. So again, we can just break it down. Joint A, we can't touch it. C, we can't touch it. B, we're gonna fix it. Same theory. So friction moments at AB equal to, I think we done these examples before. If I draw it up AB for you, again, you don't need to draw it. A 16 kilonewtons and fix B. Smart way to do it. I just going to do this one like this. Then we are happy because we done that examples, right? So what I do it, I just do this one. I just tilt it. So whatever the moments, 16 kilonewtons, we have these figures. We have these figures, friction moments of AB, friction moments of BA. If I tilt it, still will be like this. Still will be like this. Do you understand that, right? Right. So you say that, oh, this is new. You did not teach me this one. I teach this one. You just hold this one to this one, and that should be okay. Right. So we are in the positions to calculate and use our tables, because some of my students might say, okay, this case is not given in the tables, but we have given you this case. We are using this case, we can solve this one. Right. So friction moments, PL on 8 minus 16 times length 4 over 8 would be minus 8 kilonewton meters. Friction moments of BA equal to PL on 8, 16 times 4 on 8, 8 kilonewton meters. BC, we can fix B. C, pin, we can't touch it. UDL load, 32 kilonewton meters, and that is 3 meters. Friction moments of BC, which is here, minus WL square on 8, minus 32, 3 square on 8, minus 36 kilonewton per meter. Kilonewton meters, sorry. Now slope deflection equations, MAB equal to 2 EI on 4, theta A is 0, but let's write it down, 2 theta A plus theta B minus 0, no settlement, plus friction moment 8. Theta A is 0, so 2, so EI on 2 theta B minus 8, MAB, equation number 1. MBA, 2 EI on 4. I think the EI value is different here, right? For BC. Okay. Yeah, but that for BC. AB is not a. Yes.
Just yeah.
Yeah, just EI. That's right. So 2 theta B plus theta A minus 0 plus 8. Those cancels. Those cancel. So you get this one 0. You get EI theta B plus 8 MBA. Equation number 2. MBC. I think in this one we need to use second equation. As you can see, this is the case here, and we can't touch this point C. So point C is far end is if I have a BC, C if far end is pin. So we need to use that second equations. You know what I'm talking about, second equation, right? Second equations meaning that this one. EI, but then EI is 1.45. EI on L is 3 meters. Theta B minus 0. Friction moment 36. So 3 cancels. So 1.45 EI theta B minus 36 MBC. Right, and now equilibrium at B. So at B, we have two moments. One is MBA, another one is MBC. So MBA plus MBC equal to 0. EI theta B plus 8 plus 1.45 EI theta B minus 36 equal to 0. So 2.45 EI theta B equal to 28. Theta B equal to 11.43 on EI. Now we substitute back this one. MAB EI on 2 theta B minus 8. EI on 2 11.43 on EI minus 8. 3.43 kilonewton meters. MBA equal to, we have this one here, EI theta B plus 8 EI times 11.43 on EI plus 8. 11.43 plus 8 give you 19.43 kilonewtons. MBC 1.45 EI theta B minus 36 11.43 EI minus 36 minus 19.43 kilonewton meters. Quick check. This one and this ones are matching. Numbers are there, but they are inverse. Okay, so that's the answer for these n moments. And if they ask you to do the further, you can just break it down, find the reaction force as you done in the beam. Okay, and you can draw the shear force diagram and bending moment diagrams. We have 5 more minutes before we finish. Any questions? Fixed and moments, the tables I will unpack next week in the workshop. And we're going to use fixed and moments in the moment distribution methods as well. So it's good to just clear that out. I think there is a Castigliano theorem. That's we need to use it. I just need to quickly explain you that in 5 minutes. That is not part of our subjects, but that theory will help us very quick in finding the fixed and moments. It's very helpful. All right. So after, while it is fresh in your brain and is working, do the question number 3 before it can just goes away, far away from you. So look at the question number 3. Check it if you read through it, if it is making sense, what you're going to do it, where you're going to start it. And next week is moment distribution methods. Is a moment distribution was my favorite one. We will have more. We will use Excel as well in the moment distribution methods. And then stiffness methods, and that's the end of our course. In week number 12, I will revise it. I will take past years exam papers 2019, 2020, 2016, and we solve those examples. Like I'm sitting in the exam and solving, and you are watching, and then that's way you have a practice and you have some kind of a understanding. We will not going to use same examples and same patterns. Every year we change the course. Some topics are removed, some topics are added. So don't just closely and blindly follow those previous year's examples. They are just as a reference. They are not learning materials. Use your assignment questions that you have done as a revision. That's what our suggestions.
Do we know when the exam is likely to be?
I think it will going to publish soon.
Yeah.
This week or somewhere. So until I don't know, they will publish soon. But they will be in the examination period, and they are face to face. The COVID is gone, so last year they have an online, but it was invigilated. Student use. Did you use that? No.
Depend on the class. Some of them had like, you had to have the camera on, some just like.
That's right. No, not only the camera on. We have a procedure that we can see your working out. So you put your camera some distance, so we can see. That was in the COVID time. So it's kind of a invigilated. But this one is like fully strict environment. But you should be okay. We don't going to ask you something that we have not teach. If you solve your assignment questions, then they should be. Look at that questions that is we solved in the first one, right? There was nothing that we have not teach you in here. And they are not like tricky, like moment is here, or is a very, what can I say? It's a simple case. Look at these examples, right? We have not asked you anything that is we not discuss. Right? So it's doable. You just need to check it carefully. So thanks everyone, and we finish our workshop here. Let me close this recording. Stop recording.